previous talk. It is the extension of the previous talk, and I'm happy to say that the students are all here, but I've done a lot of change because they're already part of the paper. So basically, I've been moonlighting and doing some work in Minto's lab, and yeah. Let's go full screen. Control L. Control L. Full screen. Yeah. So this is, we'll be looking at, so you already discussed noise measurements in the thermally induced transition. So we'll be looking at the counterpart, which is, the physics is actually rather different, and which is what I want to emphasize here. The measurements are very, very similar. So in that sense, and the system is the same. So in that sense, it's really a continuation. It's on the same samples. So it's really a continuation of Minto's talk. And the work was done by Kalimuddin, who's really an exceptional student, who's very, very, of course, in Minto's lab. What I'm talking about. So the main message is, so I'll of course describe all of this, but the charge density wave deepening behaves like a model tipping point, and and it shows early warning signs. So that's something which I'll describe what I mean, and so that's the main message. And so as Pinto already discussed, so we're looking at this compound, which is basically a quasi one-dimensional conductor, and the charge density wave transition, which happens below 263 Kelvin, essentially leads to an incommensurate charge density wave with around 1% or so electrons, which spatially modulate, and there's an underlying small coupling to the lattice, so there's it's kind of an instability. And this system has an incommensurate phase transition, incommensurate charge density wave. And it's a continuous transition, so you can see this in the resistivity on the right axis. So you have to massage the data quite a bit actually to see this. So Minto also showed this. So you actually see a divergence in the log of resistivity versus the derivative of log of resistivity by 1 by t. So you have to really do some work to see this, but there's a clear divergence or whatever, the clear critical point phase transition 263, which Minto described in some detail, and that's continuous or weak first order transition. But what we'll be looking at is instead this field driven transition. So this again was discussed in the last talk, that these charge density waves actually form a pinned elastic manifold, and they can actually be weakly pinned by impurities. In general, they are pinned by impurities, so that the center of mass motion of the electrons is actually not there, and you have to apply a finite electric field to actually make them move. And if they were not to be pinned, then you would essentially have a superconductor, but they are always pinned. So yeah. And the spinning is been seen for a long time. So the system, for instance, has been around for 40 years or more, and there is somewhat of a revival of interest in the system, which for various reasons. Nevertheless, you can see that there's a deepening in the symmetric nonlinear IVs, which point. So of course, so this is an indication of deepening. So we'll basically try to study this deepening transition, and to emphasize that this deepening fields are very, very small, so of the order of millivolts per centimeter, millivolts per meter, so which is 6 orders of magnitude smaller than usual fields. The high field effect phenomena usually happen 6 orders of magnitude. And a simple experimentalist model to look at this deepening is to essentially look at what is called a washboard potential. So these are models which are also used for friction. And essentially, you can think of the charge density wave to be effectively pinned in a potential like that, which tilts as you apply an electric field, because the electrons couple to the field. And the current density is basically, so as Minto said, the order parameter is a 2-component object described by the phase and the amplitude, and the current density is the time derivative of the phase. So yeah. So the main point which I am trying to make here, and which is not emphasized, meaning there's, there are more complicated theories. So, of course, the original paper by Fisher does mention it, but there are far more complicated ways of people have looked at. But the main point is that we want to look at this deepening transition as a sort of a phase transition. It's a very special kind of phase transition because the singularity which it's controlled by is a saddle node singularity, which is a very elementary object when you are looking at nonlinear dynamics, but it's kind of rare in the context of condensed matter physics, as I'll try to describe why. So basically, again, as Mintu was discussing, so you can think of the simple dynamics which was described in this paper by Gruner, Zawodsky, and Shaikin 45 years or so ago. Is basically you can look at kind of a fully dissipative dynamics for the charge density wave, and the potential is this cosine potential, which is tilted by this applied electric field. And then what I can say, at some point it's easy to see that there is a critical field, maybe we can go here, where the minima and the maxima, so you have a minimum and a maximum, and the minima and maxima, as you tilt them more and more, start coming together. So these are the locations of the maxima and the minima, and as a function of parameter r, which is basically something which is proportional to the electric field. So at some point they come closer and closer and they collide and vanish. So this is called a saddle node singularity. And so that's a loss of, so basically you can think of this deepening as a loss of stability of this charge density wave, and that makes the thing move. And so this is what is in various contexts called a tipping point. And the main point about the feature of the tipping point is, as I said, so you have a minimum and a maximum, and as you change the parameter, so this basically goes through an inflection point and disappears. And this is a generic feature of, you can have locally this kind of a scenario for various kinds of potentials, and locally, so this singularity is called a saddle node, as I said. And of course, so globally there is no stable state here, so the state has to jump to another globally stable region. So usually these transitions are first order transitions. So okay. So my talk had this tipping point criticality. So why are these tipping points critical? We have to understand. And so as I said, so these tipping points are saddle nodes, and they're critical because of course at the minimum the first derivative is 0, but the second derivative also becomes 0 at the inflection point, which is also that inflection point is basically like the inverse of the susceptibility, meaning the second derivative of the potential is like the susceptibility with respect to the order parameter. So one can define, the stiffness of the potential basically goes to 0 at the inflection point. So stiffness can be sometimes called the resilience. And the basic idea, which again was discussed in the last talk, is that as the resilience goes to 0, and if you have a dynamics which depends on the gradient, so the restoring force would also go to 0, and the fluctuations would slow down, and you will have large variance and things like that. And so this is just to say that the usual first transitions which we come across are the second order transitions, which is what the charge density wave thermally induced transition also probably is. Whereas this is a more elementary object, in a sense it's even simpler. So the potential is locally like a phi cube potential, not a phi 4 potential which you have. So of course, so this is globally unstable, but locally, of course. And so of course, we are used to these kind of two minima competition, which is what happens in the first order transition. But the point is, the transitions become critical when you actually allow for this region to actually become an inflection point. So if the transition were happening somewhere here, then you would have a first order transition, but if you actually reach the inflection point, then it will be critical. And so basically these kind of transitions are supposed to be actually quite important or supposed to be describing a lot of tipping point phenomena in complex systems. And something which has been discussed over past 15-20 years is whether there are early warning signs for these transitions. This is just a sampling of some papers, in various kinds of contexts from this AMOC, the meridional circulation of the oceans, to lots of ecosystem collapses, epileptic fits. So people have tried to model complex systems using essentially the same arguments. And the early warning signs are essentially what we'll be describing in this talk. And it's basically what I'll try to emphasize. It's the same tipping point and the same kind of early warning signs which you see here. So this is what I'd said. So this is for instance, some stuff taken from some literature on this. So basically what you should see, these are essentially exactly the same things which Mintu described, although of course this is supposed to happen when you have first order, second order transition also, usual second order transition where the potential is, because there also the second derivative of the potential is basically going to 0. So all these three things should basically happen. System should have a large memory, which can be measured by some kind of correlation functions, and it would have a large variance and things like that. So measurements are actually very similar, that you look at the fluctuations, resistance fluctuations, and in this case also you can connect the resistance fluctuations. So basically you expect that the fluctuations to diverge at this critical point, and which are basically some measure of the susceptibility. Yes, this is what I said. And so this idea was first used a few years ago, or many years ago in this context, and then of course Mintu described this result. And in fact, I think your group also had actually done that. So Professor Muller's group also had actually, so I think they were the first people who had actually connected this. So the idea that although you're looking at low frequency fluctuations, and as Pratap, we were also talking that electronic time scales are 10 to 14 orders of magnitude faster, but somehow the critical fluctuations actually seem to carry through, which is quite surprising, and which people didn't really think that it's possible, seem to carry through over so many orders of magnitude close to the critical point, in fact quite far from the critical point also. So all right, so let me just come to the data. How much time have I taken?
We have 13 minutes.
13 minutes, okay, so so these are basically the time series, so at different electric fields. So one of this is around the threshold, one is above the threshold, one is below the threshold, and then I can just take that resistance time series, we just measure the resistance time series, and you can plot R delta RT and T plus 1, and if you just plot these, scatter them on a graph like this, you can see that at the critical point basically the things become more sluggish, and that's also seen by the shift in the spectral weight of the noise power spectrum to lower frequencies. So this graph is has a much higher spectral weight at low frequencies, and the correlation is also so all these are signatures of critical slowing down, pretty similar to what is seen in the thermally induced transitions also. And so indeed, for instance, this is some, as it shows, this is some work taken from complex system literature. You see basically the same analysis really goes through. And then it's, so I'll not, basically you can, so what you're measuring, what you have essentially, if you think of the changes, the change in the resistance as a function of electric field to be essentially due to the depinning, then you can think of the current to be essentially from the depinned state. Then one can basically connect whatever one is measuring to the microscopic order parameters, roughly connect them. And for instance, one expects that the correlation function would go as, so this is a quantity which you're basically measuring in experiment, and you can also roughly connect it to the measurements which you're doing, and you expect it to go as a susceptibility, etc., which would diverge or grow. All right. And so similarly, the variance would also go as susceptibility. And this is again exactly what you see. So it's, so the data are very, very similar to what one saw for the thermally induced transitions, that you see that at the threshold, the variance as well as the time scales grow. considerably. Yeah, so this is just, so spectra, as I said, so these are things which I have said that, this is critical slowing down and this is large autocorrelations. Yeah, and large enormously large variance. Okay. So now what one can do is, of course, this is done at a low temperature, not very, very low, because there's another phase transition around 90 K, which Mintu was actually published, but he didn't talk about. So around, this measurement was done around 110 Kelvin, but let's do it at different temperatures, and I'll just try to motivate as to why one is doing that. And so one can just do that. So of course, as you increase the temperature up to, so the actual transition is at 263 K or so. But you can see that up to something like 240 K, you see some vestiges of this, this critical point or criticality, the spinodal critical point. So yeah, so this is actually quite a, so each point basically here is a time series of around 30 minutes. It's a lot of data which Kalim has taken. And so then first thing which one can do is look at how the electric field, the critical electric field goes with temperature. And of course, one would expect it to go reduce. But what is somewhat surprising is the way it reduces is not some kind of an activated behavior. So the idea was that one would think that if we increase the temperature, so we have this tilted washboard, which you can think of, just this region, and as I'm tilting them, and if I have higher temperature, then I can just, do a barrier crossing via a thermal activation, and that would basically lead to some kind of an Arrhenius behavior. But what you see is actually Arrhenius would imply a temperature in the denominator, e to the power minus some T0 by T. But what you see is this fit is e to the power minus T. So it is more like, because of the motion, the jiggling motion, there's a Debye-Waller factor-like effect, which is actually weakening the pinning. So it is not so much the thermal activation, but the pinning is weakened because of some, thermal disorder. So it's more like a Debye-Waller factor-like phenomenon. This is something which, was described many years ago by Maki, and there's a more recent work in 2026 which also seems to suggest something similar. So somehow, what is happening is that you are still reaching. So basically, if you were just making these jumps across, then you would not see this divergence so well. So what you are actually, so this is what one is suggesting, is so you see some, of course, there's certain thermal activation which might be there, but the primary effect is this Debye-Waller factor like jiggling of the thermal caused by the thermal finite temperature. And so what one can try to do is think of this as a finite size effect. So one can think of temperature like a finite, so since you're working at, so basically you can think of just as if you have a finite, so what is clear is that the singularities are broadening as you're going to higher temperatures. So one can think of, so just as if you have a finite system, your critical singularities would actually, the transition would become a crossover and would broaden, and one can just make an ansatz. That's the temperature is basically like that, and one can argue a bit for that. Anyway, so one just makes that ansatz and tries a scaling collapse, which is, so here temperature is like the system size, inverse temperature is like inverse of the system size, and you can try to collapse the data, and it does seem to collapse. So I'm not sure what to say about the exponents, but it does seem to collapse. All right. So last bit is where some quantum aspect seems to come across, and so that is, so you just basically also can look at the kurtosis of these, so the fourth of these fluctuations, and so the transition, for instance, so this blue curve is actually, the transition field is somewhere here, but quite below that you see, so in the low field region, what you have is basically Gaussian fluctuations. The excess kurtosis is 0. But as you go to the critical point, there seems to be a growth in the kurtosis, which is what you would expect, because as your length scale, as the correlation length diverges, so you would, so this is again very hand waving, so you would, here basically you can think of sample as a measurement which is done over a few millimeter size sample as being incoherent sum of all these samples. So by central limit theorem, you would basically expect Gaussian behavior. But as your correlation length diverges, your sample actually acts as a whole, and you would expect, so this is what one sees, that this kurtosis, excess kurtosis actually increases. So I'm not sure what to make of this number also. And what is also surprising, or in hindsight not so surprising, yes, just stop now, is that at low temperature, so something till around, so maybe around 130 K or so, this excess kurtosis stays to a high value, and which perhaps suggests the overall phase coherence of this deepened phase. And again, it's interesting that you see, it's at the critical point, of course, the correlation length should grow. So you see that effect of a diverging correlation length or growing correlation length. But then at higher temperatures, basically the phase coherence seems to be lost in the deepened state. So there's some other experimental data which people have taken, which also suggests that this could be the case, and it happens in superconductors also. So at high temperatures, you see only this growth at the critical point. All right. So yeah. So this is what I said. So basically, this is the message which I wanted to give. So a lot of this tipping point physics. So this is like a very model system to do this. And so since I have time, maybe I'll just. So there are like other saddle node bifurcations which you're looking at. There's some new data which. So this is actually a PDF. So I wanted to actually, maybe. How much time do I have? I have. Okay, so maybe let me just see if I can show this. Anyway, so this is so there are other examples of saddle node bifurcations. So one is the spinodal point, which we've been working on for quite a while, and most recently you can think of, so you also see this thermal runaway instability in this breakdown of Mott insulators, which can also be modeled as a spinodal point. So what I wanted to show here, because the PDF, unfortunately I thought I'll not have the time, is that at some point suddenly you have this instability, which is also a saddle node, where you form a channel, and there's a certain conduction channel which can also be modeled as a saddle node. Anyway, so so basically the key point or the key message is that the deepening can be formulated as a saddle node. This is admittedly rather simplistic because there are actually fairly complicated models which theorists have been using. There is a very complicated non-equilibrium field theory which people use, but it seems to, at least as far as experiments are concerned, if one is a little stupid, you can just ignore a lot of things, and at least things do fall in place somewhat. And finite temperature seems to act like a finite size, and you don't really have any barrier crossing. It's surprising that it actually seems to, there's some long range correlations which seem to play a role along with interactions. And okay, all right, so I'll stop.
Thank you.
Yeah, questions? Yeah, Mani.
It was very nice talk. I want to, so in this 1/f noise measurement, so I'm wondering your intrinsic time scale. I think you mentioned about that, the electron which is signaling motion, what you were talking about. Those time scales are very, very short.
Those are picosecond, right? Picosecond.
You are measuring something millihertz, very long time scale.
Correct.
This could be some configurational change of a system. I mean, how they are connected? Because these two time scales, they are not even close by.
Yes.
Maybe 10 to the 10 or 10 to the 12.
Yes.
So how do I see they are connected? What you are measuring and what you are saying the physics inside?
So so that's a good question, and one bad answer would be that in theory they're supposed to be infinite, right? And infinite is 10 to the power 9 or 10 to the power 6 or millihertz, right? So that's one thing. And what you say is quite correct, but for instance, in the experiment which Mintu described, so there it seems to be a really clean second order transition. So there's no real structural transition. Also, sometimes you can think that if there are lattice effects, that even here I'm not sure in the sense, right? So you just see this, and yeah. So I mean, this is I don't know, but I mean in theory it should be there. But yeah, it's just yeah. This is what Pratap was also saying. Yeah, but yeah. So I don't know. Yeah.
Do you have a comment?
Yeah.
Two questions.
Yes, please.
One is in this picture on the left. So the tilt is the electric field. The tilt is governed by the electric field.
Yes.
The depth of the potential is given by what?
So that would be something which is so it's of course temperature dependent, as we said, because of some. So that is one of the things. Otherwise, it's an empirical quantity which is some impurity strength.
On the strength of pinning in the
Pinning,
problem?
yes, yes, and there's weak pinning and there's yes, of
Okay.
course.
Now you showed a IV character which didn't have any threshold behavior.
Well, there's a so you have to again massage out the threshold behavior. So I can show you in the sense there is a if you take the derivative. So yeah, so that's yeah. So okay, yeah,
This one
yes.
seems to be perfectly linear
No, so the red.
at this temperature.
It's not linear, right? That red thing.
No, it sort of tilts, but near the origin
Yes,
there is no flat part.
yes. So there's a background. There's always a background. So there's like a two fluid model. So only a small fraction of the electrons are condensed, if you like. So this is an
So you're saying there are two conduction channels, one
Yes,
of them
yes,
has
yes.
the pinning, the other
yes,
goes
they are normal electrons. They are normal electrons with a charge density wave. So,
Oh, really?
yes. So
Okay.
usually
But-
that's the understanding. So it's again a little naive, but the understanding is that yes.
But
So
that's not part of this model. I mean, in this model,
yes,
it will give you activity.
that would give
You go
you
to low enough temperature
yes,
compared to the barrier height.
yes.
Even if you tilt it, I don't see how you escape activation in the Langevin problem.
So meaning so that's true. So you'll get a change in resistance over. So basically this resistance is activated. Right? So this blue curve, right? So it's plotted here. The temperature, low temperature is on the right. So it's going over orders of magnitude. It's an insulating state. So it's activated, but there is no problem per se because you're sitting at a given temperature. And then you're looking at very low fields, you suddenly start getting an IV which is asymmetric, which is symmetric, and you get a nonlinear IV. And so the energy scales are small.
My point simply was I should have a flat part near the origin, then a rise,
Huh.
and then the non-linear rise. I seem to get only a linear part without any flat.
So why should there be a rise? But in the sense, why three parts? Normally there's two things, right? There's this,
Do I need a threshold field?
and then that's a
for conduction
nonlinearity.
to occur?
But there is always this background which is there.
Yeah, but the background itself is an activated object.
Yes, you are at finite temperature. So yeah,
That's okay, but look, there is always a gap in the problem.
yes.
So even the number of excited
Yes,
electrons
yes.
is going to be
Yes.
an exponential quantity.
So yeah, I don't know what to say whether what is a large number, what is a small number, right? So that's something which one has to do a quantitative. So I've just brought in ohms. So one has to see whether this is a reasonable number in terms of the actual physical system. But this is what is measured by everybody. So there is a background. There is insulating background.
I'm
Yeah.
taking too much time.
No, no.
I mean, no, because there are other people. My point is the new physics you're applying is because when you come to a critical tilt value, isn't the temperature does funny things to the problem?
No, temperature is not there. No, in the sense not important in the problem.
It's there in your noise.
Right. So that is more. So yeah, you're measuring. Yeah. So you just but it's. It's a finite temperature problem. So okay, so what is the question? So yeah, so
My point is
field is not changing the
what is
temperature.
the novelty of this? There is a interplay of funny fluctuations in this landscape.
So there's no novelty in the sense of the measurement. The novelty is basically the bottle which you're putting the data in, if you like, in the sense of the fact that you have these critical fluctuations. The two things which are novel. One is that you're actually saying that this is a tipping point physics is operational here. The second thing which was novel was the fact that you see this activated, basically this kind of finite size scaling kind of a thing. So those are two things which are novel. Yeah, you can discuss. Yeah. Yes.
The second thing is that about this time scale,
Yes.
possibly what you are measuring is not directly the fluctuation of the electronic time scale, but some domain formation that is influenced by the electronic time scale. Because otherwise 13 orders of magnitude change is not really something that one can understand.
But you consist, yeah, so that's, yeah.
Because this is the same problem, for example, that one sees at the Postales-Thouless transition. You see with this kind of millisecond noise, but it's not really understandable whether that's a real vortex fluctuation.
So what is the sort of the argument for the Postales-Thouless transition?
I don't think there is any very concrete argument, but it's probably also some kind of coherent motion formed by domains that are formed by the vortices, not really the individual vortex time scale.
So some kind of percolation physics at play, basically, you're saying.
Yeah, or something more collective.
Yeah, so, yeah, okay.
Okay, let's thank Bhaktosh for a very nice talk.